The new position lands almost exactly where it should. Almost. A single point sits just outside an older orbital curve. Close enough to ignore, then another measurement arrives. It misses on the same side. Then another. The orbit is still bending. The star is still moving through the same region. Nothing appears broken. Sagittarius A star is not seen directly here. Its gravity is... The tracked path continues across the screen beside the predicted line. For a few moments, the difference feels too small to matter. The image stays up longer than expected. No correction appears. The gap does not disappear. Decades of tracking taught observers to trust these curves. The stars still follow the pull they are supposed to follow. That part still looks true. What changes is harder to see. Each new point bends with the orbit, yet drifts just enough to avoid settling into it. The motion agrees with gravity. The shape does not. A replay makes the earlier measurements look different. The first offset no longer feels harmless. It feels like the beginning of a pattern. The star keeps moving. The fit never quite closes. Several orbital traces sit on the screen at the same time. None of them look dramatic. Each arc curves smoothly around the same invisible center. Each one appears stable enough to trust. Around Sagittarius A star, gravity is the evidence trail. One track is set aside. Another from a different observing period takes its place. The fit looks cleaner. The path follows the expected shape for most of its length. The image lingers. Nothing unusual stands out. Then, near the closest part of the orbit, the line drifts slightly away from where it should be. The display changes again. A third star appears. This one moves fast enough that a full orbit can be followed within about 16 years. The curve tightens around the darkness at the center of the Milky Way. For a moment it feels like a correction, a cleaner case, a simpler example. The same small separation appears. Not identical, not in exactly the same place, just familiar. One unusual track can be dismissed. Several different tracks leaning the same way are harder to ignore. The earlier offset no longer looks like a local problem belonging to one star. The screen fills with orbital paths again. They bend. They remain stable. They continue tracing the mass that cannot be seen. And near their closest approach, each one seems to hesitate before agreeing completely with the curve drawn for it. The updated curve arrives quietly. The old orbital line fades from view, replaced by a version that bends a little differently near the deepest part of the trajectory. Several points that once looked uncertain now settle much closer to the prediction. The display immediately feels cleaner. The revised model holds almost everywhere except the place it matters most. Near the black hole, some stars pass within only a few light hours of the invisible mass. Under those conditions, orbit calculations require additional relativistic corrections. The adjustment appears on screen. One path after another is tested against it. The agreement improves. Positions that previously seemed uncomfortable now fall almost directly onto the revised track. The comparison becomes less dramatic, more procedural. The image begins to look like a system returning to order. For a while, that feels sufficient. The corrected curve remains in place. The surrounding measurements stay close to it. Nothing obvious continues to drift away. One point does. It is not far outside the new prediction. It does not dominate the image. In a crowded display, it would be easy to overlook. The screen stays on it longer than expected. The rest of the orbit now appears reasonable. The correction explains most of what needed explaining. Relativistic modeling around the galactic center was built for exactly this kind of problem. The lone point remains where it is. Not far enough away to reject the model, not close enough to disappear into it. A clean orbital fit remains on the display, while a second layer of measurements fades in over the same region. For a moment, they reinforce each other. The corrected path still holds. The star positions remain close to where the model expects them to be. The measurements remain precise. Direct confirmation does not. The explanation seems straightforward. The orbit was refined. The correction improved the fit. The remaining uncertainty appears small enough to shrink with better observation. Another data layer arrives. The image does not disappear. The orbit does not change. The invisible mass at the center remains exactly where it was before. What changes is the interpretation. A timing pattern near the same region refuses to settle into the conclusions suggested by the motion. The orbit supports the correction. The new measurement does not fully follow it. The screen begins to compare them. One form of evidence points toward a cleaner solution. Another remains organized yet leans somewhere else. Neither appears corrupted. Neither obviously fails. Every image, track, and timing record belongs to the same evidence chain. None of it reaches the source directly. The corrected orbit returns to the center of the display. It still looks convincing. The additional measurements remain nearby. They do not disappear into the same story. The comparison layers disappear one by one. The orbital paths fade first. The timing measurements follow. The overlays that tried to connect motion, light, and prediction gradually leave the screen until only a dark center surrounded by a stable ring remains. Sagittarius A star gives the boundary a shape. The competing layers are gone. For the first time, the region looks almost simple. A final model extends toward the center. It follows the orbiting stars. It follows the bending light. It follows every piece of evidence that can still return information from nearly 26,000 light-years away. The path reaches the event horizon. Nothing comes back. The model continues only as an assumption beyond that line. The evidence does not. The shadow recorded by the Event Horizon Telescope remains on screen. Around it, the system still works. Gravity can be measured. Motion can be tracked. Predictions can be tested. Inside the boundary, confirmation ends. The event horizon of Sagittarius A star spans roughly 15 million miles across. It is not a wall. It is not an explosion. It is a limit. The earlier mismatches no longer look like isolated technical problems. They point toward the same condition from different directions. Physics remains useful. The measurements remain useful. The explanation reaches the boundary first. The evidence does not cross with it. The rule was never complete.